So here we've been given a velocity graph. So on the y-axis here, this is velocity and time on the x-axis. And we're being asked to find the displacement of the velocity function, or in other words, how far we've gone, how far we are from the starting point. So we're being asked to use a left-hand Riemann sum. So left-hand Riemann sum means that we use the left edge as the height of the bar. So that one here, in between 3 and 5, we want it has no height because we're going to use a height of 0 for that one. Okay, so I use the left edge for each one of these rectangles. That means I'm not going to use that value of 10, the right-hand value of 10 to find any areas. So once I've drawn my Riemann sums in, the area is going to represent the displacement. So in this case here, I have negative 30 meters. Okay, so that area is negative 30 meters. I get 0 meters. Between 5 and 6 seconds, I have positive 3 meters. And between 6 and 10 seconds, I have the height of 17, a width of 4. So that's going to give me 78 meters of displacement. So that's positive 78. Okay, so then the total displacement as an estimate using Riemann sums, I'm going to have positive 81 meters minus 30 meters. And so I get a total net displacement of 51 meters to the right, or in a positive direction. So any areas below are going to be considered negative. Any areas above are going to be considered positive. And that's how displacement works. For example 2, we're going to do displacement for A, but we're going to do distance for B. So we're first just going to do the displacement. So I'm going to use the area of these triangles. So in this case here, we'll say that that is at about 4. So we have 4 times 15 divided by 2. That's going to be positive 30 meter displacement. Okay, in between here, we're going to have 4, and let's say that looks like it's 7. Okay, so at 7 seconds, we have a height of 15 meters per second for 3 seconds. So that's going to be positive 45 meters of displacement here. So now I'm not using Riemann sums, I'm just using the areas given the geometric shapes. So from 7 to 15, that's a time of 8 seconds. Okay, the height is 15 meters per second, but it is decreasing the whole time. So 8 times 15 divided by 2 is going to give me positive 60 meters of displacement. For this next part here is below, so everything's going to be calculated as a negative displacement. So this is at 23, it's just past halfway. Using this rectangle here, or sorry, this triangle here, I have a width of 8, a height of, it looks like that's negative 15 meters per second. So 8 times 15 divided by 2 is going to give me negative 60 meters. So those two areas are going to cancel out. And then here I have 15, so it's 23 to 27, so a width of 4, a height of negative 15, so that's going to be 4 times 15 divided by 2 is going to give me negative 30 meters of displacement. Okay, so we have two parts that actually cancel out, and we could actually just physically cancel those out. We didn't even have to calculate them. But adding up my total positives, I end up with 135 meters, and below I have 90 meters, and so I end up with a net displacement is going to be positive 45 meters. Okay, so this is displacement. So this is A. For part B, we want the total distance traveled. Well, to do that, we're going to take each individual displacements and take the absolute value. Now we can group these together. We're going to group these together and do that, or we could just do it separately like I'm doing it here. But each of these displacements is now going to be calculated as distance. Okay, so we end up with 30 plus 45 plus 60 plus 60 plus 30. Okay, and then we end up with, in this case, it's going to be 135 plus 90, or 225 meters of distance traveled. Okay, so 135 was forward, 90 of that was backwards, but the total distance works out to be 225 meters.